So with all that in mind, let's look into the semiconductor foundry facilities and the good, the bad for the qubit applications. So for the semiconductor foundry, the good, the bad is basically foundry actually allows high uniformity, high device yield, high volume, plus 3D integration, basically complex structures. However, they are really optimized for the classical application, which is at room temperature. And on top of that, there's also the process control that allows a detailed understanding of each step. But because they are optimized for the classical application, they are not very compatible with the lab or the research lab developed method. A very pronounced example is that we can compare the subtractive patterning with the additive patterning, which is the lift-off method that has been widely used in the lab. So for the lift-off method, you first deposit the photoresist, you pattern the photoresist, and then you deposit the metal. And then you can remove or strip off the metal by the lift-off process. All those things can happen in a wet chemistry. It's very gentle to the substrate material. But however, it's not very uniform over large scale, and then due to the residues, the yield rate may also be low. For the subtractive patterning, it's essentially first you deposit the metal, and then you use photolithography or e-beam lithography to transfer the pattern down to the deposit material. And the transfer method is often by dry etching, which have very good geometry control, but could potentially damage the performance. So here is basically another example. So for the foundry in so those things are actually widely used in the research lab. One is the double angle patterning, the other is the lift-off process. So what you can have with the double angle evaporation is that you can have a clear tunnel barrier, but the feature uniformity will be large variation across the wafer. And it's only for metals that can be evaporated. For the lift-off, basically you can have the side walls and substrate protected against etching because you do not have etching. It can actually be done in the wet chemical process. But this also can result in some unpredictable metal and residues, which could limit the performance over large scale. So here, what we are trying to look at is basically a fab-compatible integration method to make our qubit structure. So here's the example that I can give. For example, that's the superconducting qubits. And just a quick reminder, typically the junctions are made by the shadow evaporation. But in the fab method, it can be the tri-layer junction approach or the overlapping junction approach. So basically you can deposit different layers and then you etch them away. Sorry, something I forgot to mention. So if we look into the electrical performance of those things, the uniformity is really good. Another example is basically if we look into the fab-compatible spin qubits. So if we start with our spin qubit structure, the typical spin qubit structure is actually the overlapping structure. So similarly, we can define the gate layer by the subtractive patterning, and then we etch away the remaining metals, and then that's how we have the gate layer 1. If we repeat this process, then we can have multiple gate layers. But however, the etching or the removal of the gate layers essentially could damage the interface that qubits really sit at. But the advantage is essentially a very good uniformity. If you take a long cut across our qubit device, then we can see very good dielectric uniformity between the gates. And if we take the CDSEM across the device on different gate layers, and if we measure their dimension across the wafer, then we can see the standard deviation is around 1 nanometer. That's very good geometry uniformity can also translate into very good electrical uniformity. So if we measure the threshold voltage of the barrier gate or the top gate of a single electron transistor, which is needed for for spin qubit operation, then we can see very good uniformity on the threshold voltage. Another aspect is basically the high production volume and also the yield rate. Essentially, on the 300 millimeter wafer, we can fabricate more than 10,000 qubits in each batch. The turnaround time is maybe on the month scale, but we can have multiple wafers running in parallel. On the yield rate side, we can actually calculate that at room temperature by a probe station. So if we focus on the spin qubit again, one of the limiting factors is the device yield and also the device uniformity. And here we can already get a feeling at room temperature. Basically, we can look into the effective oxide thickness across different layers, and we can see they almost sit on top of each other. And if we look into the leakage between the gates, that's also the limiting factor for the qubit yield rate, and we can see the yield rate is almost 100%. Okay, now we can look into the second part. It's basically, okay, now we can make the device. How can we make the device better? That crucially relies on the material exploration. That's an example of the native niobium oxide. When you deposit them and when you make the resonators, then they will have some oxide form at the interface. By looking into those oxides, actually we can identify those oxides. That also allows us to optimize them. So here, maybe just really fast to flash that through. So we have the reference, which is performing like that, but just by different optimization or different waiting time, we can really investigate the formation of the oxide. And we can also achieve a Q factor of 7 million in the single photon regime, and we can also identify what is the limiting factor for the Q factor loss. Okay, for the spin qubit, what we can do is essentially we take the spin qubit structure, and by process optimization, in the beginning we can have a lot of disorders in our qubit dot formation, but by optimizing the process, we can really achieve the single electron regime very nicely. So the way to do that is we can change the gating material from the tinitride into polysilicon, but here we also show that the dielectric, the deposition, the etching, the cleaning, all those fabrication steps do matter, and we can calculate them by the whole bar mobility, and we can see a clear difference. So that means to achieve full or good qubit performance, we really need full gate stack optimization. And on top of that, I also want to highlight the knowledge or the characterization knowledge developed for the IC industry can also be used for quantum computing. So at room temperature, we can actually find a nice correlation of the transistor GM to the noise performance, basically a noise characterization. And that means the limiting factor is Coulomb scattering. And we also can find a linear correlation of the normalized GM to the quantum, to the whole bar mobility at in the sub-Kelvin regime, which also allows us that, or is an indication that we can use room temperature metric to assess the interface performance at low temperature, and we can also get an understanding of the limiting factor, the true physical mechanism. Okay, so toward that further improvement, what we can also say is basically the process-induced damage due to the subtractive patterning. So if we want to make our silicon substrate, or the first gate layer, we start with the silicon, then we grow very good thermal oxide, and then we put gate layer 1. So that's how our gate layer 1 mobility is really good. But however, if we look into higher layers, they are not ideal. Why is that? It's because when we are making the higher gate layers, because it's subtractive patterning, we need first to remove or etch away gate layer 1, then we put the isolation layer, then we put gate layer 2. Similarly, we can do that for gate layer 3. So you can see the mobility actually dropped for the higher gate layers. So we can actually optimizing the etching process, so the gate layer 2 performance can be recovered. But for gate layer 3, because it sees more etching, and on top of that, there's also the deposit silicon oxide, which is not ideal. So if we change that to the high temperature oxide, the gate layer 3 mobility can also be recovered. Okay, so now let's look into the final aspect. Basically, the fab technology also allows upscaling architecture. So what does that mean? When we are looking into the advanced fabrication, one is basically the further downscaling requires that the structure is more aggressive, and also the trench of the fin can also be reduced. And on top of that, the metal connection can also be very complex. And on top of that, we can also introduce some normal features. For example, the magnet nanopillars, which will be used for magnet tunnel junction, it can also be helpful for spin qubit control. There also are the superlayers with an aspect ratio of 10:1, which allows you contact very deep features. On top of that, there's also the N-type, N-FET and P-type. So essentially, they call it C-FET. So you can have 3D stacking of the transistor on top of each other. So that actually allows the consideration of really advanced qubit structures. For example, that's the stacking of the qubit layer in the bottom and also transistor on top. The second consideration is that with the fab, you can use advanced gate patterning. So essentially, the gate patterning has been developed for a lot of the technology node. By optimizing the process, essentially you can have very narrow or very small line edge roughness. So here I have to remind you, the numbers are actually the 3 sigma. So that can improve the fundamental by improve the fundamental understanding, we can achieve very good uniformity. And that also allows the implementation of a shared control structure that requires highly on the uniformity. And finally, there's also the development of the 3D stacking or the 3D integration. So you can actually stack or glue different wafers or different chips on top of each other to extend the functionality. And similar concept has been proposed for superconducting qubits, and then for one of the several advanced qubit structure or qubit chip implementation, they are already using it.